Hi, my name is Simon Kishek, and I'm the Electrical Test Engineer here at Haydon Kerk Motion Solutions, business unit of Amatec Precision Motion Control. For this video, I will introduce you to the IDEA software, an interface designed to program the IDEA drive, a constant current stepper motor driver. The IDEA software is an intuitive graphical user interface that will allow you to get your stepper motors in motion within minutes. The IDEA drive utilizes a serial communication line to allow users to control them directly from a PC. Forget toggling dip switches to change between current levels or step modes. Avoid learning command sets and figuring out how to set bits or program a slew of microcontroller registers. The IDEA drive was designed with the end user in mind, allowing for fast prototyping to keep you focused on your designs rather than figuring out how to perform a move with the stepper motor. Each command sent to the drive couples the entire move profile, allowing you to manipulate various move parameters on the fly. So let's start off by connecting the drive to the PC. Here we have a PCM4826E drive utilizing a USB communication along with NEMA size 17 motor mounted on one of our BGS rails. Since we are using a motor with a 5-volt winding, the drive will be powered with a 40-volt DC power supply to maintain an 8-to-1 voltage ratio between the supply and the motor. On program startup, the user will see the following screen. The GUI is designed with a part number system to aid the user in motor setup. Again, this part number is for the type of motor which will be used. The software will automatically detect which drive is connected. There are two main functions of the part number system: to limit the amount of current that the drive outputs to prevent overdriving and causing damage to the motor, and to set the resolution of the linear actuator. This allows users to not only work in units of steps, but inches and millimeters as well. Avoid calculations between pulses and travel distances, and work within units that you are comfortable with. There is even an automatic conversion feature built into the software which will convert programs between various units. So if a user creates a program with units of steps, another user can read the same program in units of inches if they select those units on program startup. The program was designed for both mechanical and electrical minded users. I will start the interface with a part number for our size 17 motor and select inch units. Since I will be using a rail, there is a B prefix to the part number and a 0 for the resolution. The 0 indicates that there is a rotary motor rather than a linear actuator. This will cause a second window to pop up, which will characterize the rail and allow the software to calculate the step resolution for the motor from the lead of the screw. Users have two ways of controlling the drive, either in real-time or program mode. In real-time mode, a serial connection is maintained between the drive and the PC. Users send commands to the motor and witness motion instantly. This mode is great for observing how a motor will react when various parameters within the move profile are modified. In program mode, the user will create a program and download it to the drive, where the microcontroller will execute it from memory. Rather than performing a single command at a time, the user can create an entire procedure. Once the program has been downloaded, the user can then set it as a startup program where it will automatically run on drive power-up. This allows the drive to work without maintaining a connection to the PC. In either mode, the drive utilizes a trapezoidal move profile where the following parameters can be modified: start speed, end speed, acceleration, deceleration, and an optional 30% current boost during ramping to help the motor overcome inertia when initially setting the load in motion. The communication structure is set up in a fashion where each move command contains the entire move profile. So in addition to the move parameters, the following parameters can also be modified: current levels, both run current and hold current, as well as step modes all the way up to 1/64th of a step. We will start off in real-time mode with the following moves at our disposal: a go at speed command, which actuates the motor to run indefinitely at a particular speed; an index command, which actuates the motor to move a finite number of steps; and a move to command, which actuates the motor to move to a relative location. There are two stop modes: stop command, which stops the motor using a ramp, and an e-stop command, which stops the motor immediately. In addition to the moves, the following functions are also available in real-time mode: setting position of the drive, toggling inputs and outputs, activating an encoder for feedback, and a software reset. Keep in mind that all functions within real-time mode are available to program with. Program mode has additional logic functions that are not possible when working in real-time because they are available on the microprocessor level, relying on interrupts and memory addressing. So let's perform a simple extend move with the following parameters. We'll extend 10 inches at 1 inch per second using the rate of current of the motor in full step mode. Well, that move was a bit loud due to the vibrations in the motor while stepping. So let's smooth it out with a finer step mode. So I'll retract with the following parameters. Retract 10 inches at 1 inch per second using the rated current of the motor in 1/32 step mode. That run was smooth, although perhaps it is running too slow. So let's increase the speed. So we'll extend 10 inches at 6 inches per second using the rated current of the motor in 1/32 step mode. The motor is struggling to move this fast, so I need to incorporate some ramping in order to be able to run at this speed. So I will extend 10 inches at 6 inches per second using the rated current in 1/32 step mode with an acceleration of 5 inches per second squared. I like the way that runs, although I have some momentum at the end of that move, as you can witness by the spring that I have attached to the carriage on the rail. So I will complete my move profile by including a deceleration ramp. So I will extend 10 inches at 6 inches per second using the rated current of the motor in 1/32 step mode. But this time I will have an acceleration of 5 inches per second squared and a deceleration of 5 inches per second squared. That looks great. Now that I have created a move which works with my application, I can go ahead and continue on to the next step in my project. And there you have it. I was able to effortlessly change various parameters of my move profile within minutes. And I did all this without having to know the rated current level of the motor or how many pulses it takes to travel a given distance on the rail. The software will even highlight input boxes for the various functions when the user has entered invalid data based on the part number. Thank you for joining me. We will cover the programming mode of the software in part 2 of our introduction to the IDEA software video.